Hello, everyone. Welcome back to the second session of the Boeing Quantum Creators Prize Symposium. Very excited about this session. My name is Felix Leditzky. I'm an assistant professor in the math department at University of Illinois Urbana-Champaign. And co-moderating with me is Zoe Yan, assistant professor at the James Franck Institute and Department of Physics of University of Chicago.
Hi, everyone. It's my great pleasure to welcome our first speaker of the session, Adam Shaw. He is joining us from California Institute of Technology, and he'll be telling us about fingerprints of randomness on a 60-atom quantum simulator.
Yeah, so thank you to all of you for being here to see this talk. Thank you to the organizers for inviting me. And today I'll be telling you about some of the work I've done during my graduate school career, sort of using a large-scale quantum device to study large-scale quantum physics. So to start out, I just want to frame sort of a fundamental challenge in quantum science, which I'll call the entanglement challenge, which essentially is no matter what type of quantum science we're studying, we generally start with some simple initial state. And then what we want to do is basically apply some sort of generally unitary evolution to our system and produce some useful entangled state, which we use for computation, simulation, metrology, et cetera. And I'll distinguish that there's different ways in which you could imagine doing this evolution. You could consider this with digital gates, like you might think with a digital quantum processor. You could do this with like just a simple Hamiltonian that you apply over time in more analog quantum simulation context. And I'll get into both of those throughout the talk. But what I really want to emphasize here is that both of these different ways of doing this sort of process are fundamentally the same in that they're both succumb to the same type of problem, which is errors, which is in modern quantum systems, we always have errors occurring in our systems which generically change the output of our device. And so a fundamental challenge that we face is that we're trying to make larger and larger quantum systems so we can use more and more entanglement, but that also means that errors become more likely. And so it's a question of how do we control these large systems, and particularly for my talk, how do we verify that we've actually done the correct quantum evolution with our system? I am an experimentalist, and so the experimental platform which I use, very briefly, is a Rydberg atom array. We already heard a little bit about this from Pi this morning. Essentially, the idea is you take a tightly focused laser beam, and it can trap a single atom at the focus. Then by using many of these laser beams, you can create arrays of atoms in 1 dimension, 2 dimension, even 3-dimensional structures. Then we can actually make these atoms interact with each other, like we need to do for quantum computation, quantum simulation, by using so-called Rydberg interactions. We bring 2 atoms close together, we excite them to some high-lying electronic orbital, and this actually means that we basically spread this one excitation across 2 atoms, forming a Bell state very naturally with just a simple laser pulse. This has been pursued for a number of years. So we're happy to say that just as of last month, we basically showed a record entanglement fidelity of this Bell state generation using that erasure conversion method that you heard about this morning, and we're able to reach 99.9% 2-qubit entanglement fidelity with these neutral atom systems. And what's really exciting is that we have an error model for a system which is very realistic, which shows that 4 nines of fidelity is actually quite achievable. But 2 qubits is nice, but it's not that interesting because, of course, you can simulate 2 qubits on a cell phone. What we really care about is what about larger systems? So to give context for the rest of the talk, we're going to be talking about a 1-dimensional array of atoms, and we're going to be thinking about this in a quantum simulation context. So we're going to think about just evolving these atoms under basically an Ising-like long-range Hamiltonian. If you do this with no errors, you should get out some pure state psi. And the dynamics that we care about is basically that the half-chain entanglement entropy of the system grows linearly and then saturates as a function of system size. Of course, this is not actually what comes out of our quantum device, because in reality we do have errors. So the output of our device is some noisy mixed state generically. And the quantity that we care about is basically the fidelity between these 2 states, which in simple terms is just the probability that we didn't make any errors when doing this quantum operation. Measuring this fidelity is very important for understanding quantum systems. It's also extremely difficult because to measure this, you actually have to reconstruct this density matrix rho. And this is basically impossible because it requires an exponential number of measurements. And so it's impossible from like 2 qubits. And so a lot of work in the field in recent years has been how to estimate this fidelity, which is actually central to Google's claim of quantum advantage in 2019. Google's way of doing this actually doesn't really work for quantum or for analog quantum simulators. So we spent a number of years adapting their methods to work for a much broader range of devices. Essentially, the idea, in very brief, is that you basically program this Ising-like evolution to be very chaotic so that small changes in your system, like errors, cause large changes in some output observable, like the probability of measuring different bit strings. And then we can compare the bit string distribution with and without errors, and with that we can basically just say that the fidelity can be estimated by some probability correlation function between the theory and the experiment. This is just sort of background. I can actually show you that this really does work. First of all, with just simulation. So we can do 2 simulations of our system. One where we have no errors in our system. And then the other simulation, we use our noisy error model to basically simulate what we actually think the real experimental errors are. And you can see this really beautiful agreement in terms of both system size and time at a single system size between the fidelity that we actually measure in the system and the fidelity estimator, which we can actually then measure with simple observables. And then, of course, I can basically put experimental data on the same plot and show that with just a very few number of measurements, what we're actually able to do is measure the fidelity for up to a system size of 30 qubits, the probability that we made no errors with the system of around like 40%. This is already quite exciting and was very exciting when we had this work done, but I'm kind of hiding something here because this plot is stopping at 30 qubits. The reason for that is to do this operation, we basically needed to have this exact classical simulation of our system. But of course, the whole point of quantum science is to really go beyond the regime where we can do those exact classical simulations. And so again, we have this question, what about larger systems? To get into that, I kind of want to actually take a step back from quantum science and really think about just like classical computers for just one moment. And I want to ask, what makes classical simulation of quantum systems hard? We all know that sort of classical computers are actually very good at simulating quantum systems as long as they're below some critical threshold around 30 qubits. It turns out there's another regime in which they're very good at simulating quantum systems. And we can sort of think about this by looking at how entanglement grows in these systems, where at early times, whether there's 5 atoms or 10 atoms or 1,000 atoms, you just can't build up that much entanglement in these local systems. And so what that means is that there's been a lot of work over the last 20 years in sort of doing classical simulation methods which make use of this process to simulate essentially arbitrarily large systems out to some finite time. These are known as tensor network methods, just to get technical. And in one dimension, these are specifically known as like matrix product state methods. And all you really need to know is that it's controlled by a single parameter, the bond dimension, which sets a cap in how much entanglement the classical computer can simulate. And once the entanglement surpasses that cap, the classical computer becomes inaccurate. You can sort of think about this as a relatively simple phase diagram where the classical computer is exact or the classical computer is approximate. And we can think about benchmarking our system in these 2 regimes. We've already seen that when we're in this sort of classically exact regime, we're able to benchmark our system because the entanglement never surpasses some simulation cap given by the bond dimension. That means the classical simulation fidelity, the accuracy, is always 1. And then we see some exponential decay of quantum fidelity because of errors. This changes if we now use a bond dimension which is too small in our classical simulation. Because now, after some certain point where the entanglement grows too large, now the classical accuracy also drops, and at the same time, the benchmarked quantum fidelity also decays because what we're essentially looking at is like a cross-correlation that includes both the experimental fidelity that we care about and this classical fidelity that we really don't. And the real important point here is that as we go to larger system sizes, we aren't able to use a high enough bond dimension to do this exactly in any realistic classical computation. But the important point of all this is that actually what we can do is extrapolate this as a function of that classical resource because we see this as a smooth function of a classical resource. So we can actually use many different classical simulations, none of which were accurate, and we can extrapolate what the quantum fidelity would have been if we actually had an accurate quantum simulation, a classical simulation. So if you're familiar with the term, it's a form of like zero noise extrapolation on the classical computer. That's a little bit technical just to sort of show that this really does work. We can actually do this resource extrapolation to estimate the fidelity for system sizes as large as 60 qubits into a late time regime when the entanglement entropy is basically maximal. You can immediately see there's something a little bit odd happening as we go to these large system sizes. At small system size, you sort of looks exponential decay, and then as you go to 42 and then 60, this starts bending at sort of late times. We actually, from this, learned that one of the chief error sources in our system leads to non-exponential fidelity decay because of certain non-Markovian noise sources. All that to say that this was not at all expected when we started this work, but just by doing this sort of error probability measurement, we actually were able to learn about our system and able to learn how different types of noise affect our system, which now we're using to do noise learning processes and a whole host of other error correction type schemes, which I can talk about at the end. The point in general is that if you sort of just consider the quantity of interest we care about what is our fidelity to create a state with maximum entanglement entropy that can be used as a resource for simulation or computation or sensing. And the point is really that we can achieve about a 10% fidelity of producing a maximum entanglement entropy state with a system size of n equals 60. 10% is a bit of a hard number to sort of know what it means. I'll give 2 pieces of context here. One, this number is consistent with a 2-qubit entangling fidelity of about 3 nines, which we have. The second thing I'll say is that while there's obvious problems in this comparison because of controllability and dimensionality, when Google claimed subquantum advantage in 2019, they did so with a fidelity of 0.3% with 53 qubits. That was on a digital quantum processor. Here, with this analog quantum simulator, we're able to achieve a much higher fidelity for even a larger system size. And it kind of points to the fact that, with these analog quantum devices, though they're not able to do sort of general quantum computation tasks, for the specific problems of interest that they can actually implement highly efficiently, we can actually do those sort of tailored applications extremely well. And we can't just compare just against Google or just against our 2-qubit fidelity. The thing that we actually sort of really care about is comparing against not just a quantum device, but against a classical device. Because now we can say that the quantum system isn't able to perfectly simulate a 60-atom quantum system, but also the classical computer also can't perfectly simulate it. And so what we want to look at is basically what are the minimum classical resources that we need for the quantum device, or for the classical computer, to be better than the quantum device. We can do this computation, and what we basically see here is this essentially exponential growth of the classical cost required to actually beat our experiment in terms of fidelity. I know that this y-axis here might not be too familiar to people, so I'll sort of put one data point on here, which is that for this last data point at 60 qubits, to do the classical simulation of our system at this point would require around 180 days on the Caltech supercomputer to run. That has to be qualified in a couple of ways. First of all, you might naturally ask, maybe you just have a really bad classical simulation algorithm. And there's no way to answer that question definitively, unfortunately. I can just say that we tried a lot of classical simulation algorithms. We tried, for instance, Google's simulation algorithm, this path integral formalism. We tried many of sort of state-of-the-art algorithms. And actually, none of those are even shown on this plot, because all of them, quote unquote, failed well before the 60-atom limit. And so we actually had to invent a new type of sort of matrix product state algorithm that was very efficient and highly optimal for the Rydberg long-range one-dimensional dynamics that we study here. So all that to say that we think that we are really using a good algorithm for this study. The other thing to note is that this 180 core days is clearly not a statement of advantage with our quantum simulator. But it also doesn't exist in a vacuum. You could put this exact classical simulation on a computer with 1,000 nodes, thousands of cores, and get this to be hours or minutes. But I can also, over time, improve my quantum device. And if we look at how this classical simulation time changes as a function of essentially that equivalent 2-qubit fidelity of our system, right now with around 3 nines of fidelity, like I was saying, it's about 180 core days. As I now go to a little bit higher in fidelity and all the way up to that 4 nines of fidelity that I told you was very possible, we basically go from 180 days to 100 years and very quickly to the age of the universe in terms of the classical simulation time. And to me, this is just conceptually very interesting, because when Google claimed quantum advantage in 2019, the way they did that is basically by engineering a highly complex 2-dimensional random unitary circuit with a digital quantum processor, the entire point of which was to make a task that was as hard as possible to simulate. Whereas what we're doing here is time independent, it's global, it's one-dimensional, it's basically the simplest type of quantum evolution that you could possibly imagine. And that even for this system, we're quantitatively entering a regime where the classical computer can't keep up with the quantum device. I think that fundamentally this is interesting for a number of reasons. It also has a number of applications which are of general interest. I'll go into them just very briefly. So you can use this sort of fidelity estimation system in order to do Hamiltonian learning, to actually learn the parameters of your Hamiltonian and learn if there are sort of parameters in your Hamiltonian that otherwise you would have no way to estimate. And we've shown this both on sort of a single site level and globally over the entire system. I mentioned briefly in the middle of the talk that we have this new protocol for noise learning. Basically, when you can measure the probability of errors happening, you can actually figure out which errors happened when and actually determine sort of what are the different error sources affecting your system in a way that is really impossible with any other sort of many-body spectroscopy means. We're actually developing this a lot more at the moment to really be able to apply both to analog quantum simulators and digital quantum processors. There's some interesting many-body physics, and maybe the last thing that I'll say is just that we have this new protocol for entanglement estimation, which I think is one of the most interesting things that comes out of this. It gets a little bit technical, so let's go very quickly. Essentially, all the entanglement I've been talking about today has been pure state entanglement. Doesn't really matter what the difference is between pure state and mixed state, but the point is that the mixed state entanglement entropy of an experiment, of a real experimental system, is something that's notoriously hard to measure even theoretically. By sort of synthesizing a lot of different works from a lot of literature, we're basically able to find a very simple estimator of the actual entanglement content of an experiment, just with this very simple formula here, and you can see this nice entanglement growth measured experimentally. The whole reason why I think this is important is because this formula doesn't just apply for our analog quantum system. You can do the same exact thing for digital quantum processors, such as those used in supremacy or in advantage measurements in recent years. And you can basically see that for the first time, we have a quantitative measure of putting both analog quantum simulators and digital quantum processors on the same plot and on the same map. So I really think that in the next couple of years, as we improve these quantum devices and sort of generally improve the field of quantum science, there's going to be this major push in the NISQ era of understanding what can we do with quantum devices, both simulators and computers, and what sort of useful applications come next. And I think there are many. So all that to say, I think that measuring errors on a quantum simulator or quantum computer is very important because you can really learn about your system. And only by learning about your system can we then improve them and actually reach that era of fault tolerance that we're all looking for and hoping for. So with all that, again, thank you to all of you for sort of listening. Thank you to my collaborators, both experimental and theoretical. And yeah, happy to take any questions.
Thank you for this really nice talk. Any questions? Yeah.
Thank you for the great talk. I was wondering whether you can comment more on how to learn about the noise or decoherence in the system.
Yeah, it's a great question. So I don't know, can I go backwards here? Oh, wow, great. Yeah, essentially the idea is that there's two different ways to do this. One, we already sort of learned about the noise just by doing these fidelity measurements because we saw this non-exponential fidelity decay, which wasn't predicted by sort of Markovian type noise models. And it was only after we saw this, basically backtracked through our error model, we identified, oh, these certain non-Markovian noise sources actually cause this fidelity decay. And you can tell how much Markovian versus non-Markovian noise you have just basically by looking at how different you are from an exponential fidelity decay. That's one thing. On the more sort of, I guess, interesting front, you can actually, doing the same exact process that we do for this fidelity estimation where we basically measure bit string probability distributions, you can actually look at the shape of those distributions, and it's kind of being shown in a somewhat confusing way up there. And for the same fidelity, these distributions of probabilities will look different depending on what different error sources are affecting your system. So if you have sort of local errors or global coherent errors or some combination of the two, just by looking at basically how probability distributions concentrate due to quantum errors, you can tell what those errors are. And we're still actively developing this both, but it works both for sort of digital quantum processors and quantum simulators.
Thank you.
Yeah.
Very nice talk, thanks. You mentioned that you can use these ansatz to actually learn the Hamiltonian and like get a more accurate description of it.
Yeah.
Do you think that could feed back to actually improving the classical simulation? Because a lot of these methods use features of the Hamiltonian, right?
Yeah, that's a great question. I guess there's 2 points to that question. One, certainly, what we do here is, we first pre-calibrate all of our Hamiltonian parameters. We sort of do the best we can experimentally. But honestly, this sort of Hamiltonian learning type protocol, the way it works is that you run your experiment, and then you measure the fidelity against a classical simulation with some varying Hamiltonian parameter. And so you're basically seeing when the classical simulation best matches with your quantum device. And so in that sense, we use this all the time for our Hamiltonian learning at this point. And it really does sort of optimize the classical simulation to best match the experiment. And something that I think is maybe overlooked in this is that, of course, I say that we're doing some time-independent dynamics. We're not really doing time-independent dynamics. There's some turn-on time of all of the lasers. There's some transient dynamics that must happen at some level. And so we're effectively learning like the best classical model of our experiment. And I think that that's something that's very interesting and that we're pursuing more is that you can really tailor the classical model that best overlaps with your true quantum dynamics. If that answers your question. Yeah.
Further questions? I have one.
Yeah.
Maybe what are the experimental steps to get beyond 60, or do you think that that's maybe not even a relevant question now given the lag between these classical estimators?
Yeah, no, I think it's a super relevant question. I think that why did we stop at 60 here? There's kind of 2 different regimes. One, we're doing everything in 1 dimension here, and the reason we're doing things in 1 dimension is pretty much explicitly because classical simulation algorithms are so good in 1 dimension that we wanted to make this very quantitative comparison. Once you go to 2-dimensional systems, the classical algorithms in general become a lot worse and a lot harder to sort of run. So first of all, we think that just going to 60 atoms in a 2D system will already make this a lot more difficult. But then certainly sort of going to much larger systems, we think even in 1D or 2D, we'll be able to keep doing these comparisons. We're able to do some scaling arguments and basically show that we think that our methods should work for up to like an order of magnitude more atoms to very efficiently measure the fidelity. So in that sense, I think that there's definitely room to play on in terms of going larger, and you just sort of get higher and higher in this plot of how much classical resources you require to beat the quantum device.
What is the source of the non-Markovian noise in your system? Because typically we think of noise as kind of a Markovian model, right? And
Yeah.
so where does it come from?
I would say basically everything is non-Markovian actually for our system. Well, essentially the idea is that things that are Markovian are things like atom decay, things that you generally have no memory about the quantum state. But for instance, if I have a laser addressing my system, that laser might, on every different shot of the experiment, have a slightly different intensity. And then it's sort of like a time constant error over a long time. And that's the sort of non-Markovian noise that actually leads to exactly this type of bending. You can also have non-Markovian noises coming from basically the atoms have some finite temperature. And so the atoms are moving around a little bit, and that changes their interaction strength. You can actually figure out the form of this. And this is also this non-Markovian noise source that gives a different but very similar type of fidelity decay. So most of sort of the error sources that we encounter have some degree of non-Markovianity, maybe. But I think that one thing that's important to point out here is that even for sort of the digital quantum processors, like for instance Google's quantum processor, where there's kind of this conventional wisdom that it's all some Markovian decay. Even there, you have these coherent control errors, which you can actually you can look in the Google supplement from 2019. You can see some amount of non-Markovian or at least coherent control errors in their system. So I don't think this is sort of specific to analog quantum simulators. I think that generically for pretty much all quantum devices, there's going to be some degree of non-Markovian noise in the systems.
Let's thank the speaker again.
All right, next up is Yu-Hao Deng, a PhD student at the University of Science and Technology of China and currently visiting the University of Chicago. Please.
Okay, great. It's truly an honor to be here to share you with our research on quantum computational advantage with photons. Let me begin with the basic fundamental scientific motivation of our research, that is the extended charge-Turing thesis. So this thesis is from theoretical computer science, which states that any reasonable model of computation can be efficiently simulated on a probabilistic Turing machine. So basically that means a classical computer can simulate any reasonable computational models. If you look back to the history of computer science, this is always true. From the ancient calculation tools to today's GPU, which even ChatGPT are based on. This is always hold true. The only counter example we have today is a quantum computer. But so far we cannot physically realize a quantum computer. So there are several steps to really do for the blueprint of a quantum computation. From beginning of the demonstration of single qubits and two qubits operations to quantum computational advantage, and maybe finally to a universal quantum computer. So currently we are at the point of quantum computational advantage. So what does this mean? Quantum computational advantage means that there are certain specifically designed problems that are well-defined mathematical problems, which are you can use quantum computer to efficiently solve them. But on the other hand, for classical computer, it will take overwhelmingly long time to do that at the current stage. And there are two candidates for this problem. The one is boson sampling, which is suitable for photons. The other is random circuit sampling for superconducting system. And we also saw exciting results from Twizzler atom array progress recently. But the first two early claim of quantum computational advantage experiments, one is from Google, the Sycamore in 2019, and the other is from our team working on boson sampling with photons from USDC and in 2020. So today I will talk about our experiment on boson sampling. Before I go into the boson sampling details, I want to first let you know that during these years of research, one thing we realize is that a quantum computational advantage is a continual competition between the quantum hardware side and also the classical and algorithm community. After the first release of this experiment, there have been significant improvements on the classical algorithm that can simulate the experiment much faster. So today we would say that a quantum computational advantage is not a single shot event. Actually, it must be ultimately established through a continual efforts. We have this confidence because we know the quantum computer has some scaling argument that has advantage. So in the long future, we can definitely have more and more stronger and stronger evidence for this. And that's also one reason we are continually pushing our experiment. Okay, so what's the Boston sampling? I'll begin with a very basic physics picture of this, which is a Hahn-Mandel interference. So this is a very elementary quantum optics phenomena. Basically, there is a beam splitter, and if you have one particle input into this beam splitter, let's say it's a photon input this beam splitter, you have 50% of chance transmission and 50% of chance reflection. So now suppose you have two classical particles input into this beam splitter, as shown here. You have 4 output cases, and they all can happen with equal probability. But now consider you are using photons, which follows quantum statistics of bosons. The photons will be indistinguishable, and you will find that 2 out of these 4 cases actually interfere deconstructively. So what you will observe after the beam splitter is the 2 photons always exit from the same output port. And this is the most simple, multiphoton interference. And boson sampling is just a generalized version of this process. You can think of that you have many single photons input into a large array of this beam splitter network, and the output is actually a highly entangled state. And if you calculate the probability of the output, it is related to the mathematical quantity called the permanent of this matrix corresponding to this this interference network. And the classical complexity to calculate this quantity called permanent scales exponentially with the number of single photons. And there are also theoretical arguments from Scott Harrison on that the sampling problem itself is also hard. So not just calculating the quantity, but also sampling from this distribution is also hard. And that's the problem of boson sampling. So boson sampling has been proposed for 10 years, but for the past 10 years before our experiment, the experiments are all still far away from quantum advantage. The reason is most previous photonic experiments restrict themselves to the single photon regime. So they only input the single photons into this network, and this is actually just a tip of the iceberg. We can actually, people later realize that if we replace these single photons with another quantum source, that's squeeze state, you can actually also do a boson sampling, which is called Gaussian boson sampling, with the same computational complexity argument. So this is what we do in our experiment. And here is our overall scheme of our experiment. There are basically 4 parts. 4 modules. The first is the quantum light source, which we create this squeeze state. So we create 50 such squeeze state, and we input them into our experiment with active phase locking. So this is done on a 1/100 lambda precision. So all optical active feedback phase locking, and all these photons are input into the interferometer, which is I guess the largest in the world, and it can have very good mode overlap and interference, and it's a big job. And after all, we detect all these single photons with superconducting nanowire single photon detectors with 100 such devices with an average quantum efficiency of 90%. So because of this time limitation, I will not go to the technical details, but I want to present you with our results. So think about this. This is actually a very interesting question. We are already in the regime of quantum computational advantage. So by definition, a classical computer cannot simulate our experiment. How do we know we actually do our experiment correctly? So our strategy is, first we look at the subsystem. For a subsystem of our experiment, the simulation is classically easy, and we can check whether the two agree with each other. And we find, well, they agree very well. So with that, we have some confidence, and we can go on to the classical intractable regime. So how do we do the validation in this regime? The strategy is we use some statistical tools to somehow efficiently validate that our experiments are not done from some wrong hypothesis. Like suppose your experiment have some noise that makes it classical. What can this hypothesis be? And we just exclude all these possibilities. So for example, we exclude the uniform distribution and also more non-trivial distributions like thermal photons input, distinguishable photons input, and we can all exclude them by like photon number distribution, to second-order correlation functions, and have output generation. So these are all statistical tools we have. And with that, we can say our experiment agrees pretty well with the ground truth, but this mock-up distribution, they failed to do this. So with that, we are able to provide evidence of quantum computational advantage for this experiment. So we reached like 76 maximum photon number in this experiment. And at that time, the best classical algorithm running on the supercomputer would take 2 billion years to simulate this process. And that's our first generation of experiment. So the major limitation of this experiment is that we have limited efficiency of our experiment. It's like more than 30% of efficiency. And that means, in photonics experiment, if you have limited efficiency, this will cause your photon loss, and that leads to decoherence, which is something we don't want. So our major improvement in our second generation is we developed a laser-inspired stimulated squeezing light source. So this increased our source brightness by a factor of 3, and also a lot improvement on its efficiency. So with that, we also upgrade our experiment to a larger scale, from 100 modes to 144 mode, and with that we are able to arrive at more than 100 photons experiment. And we also developed the new validation tools to better characterize whether our experiment are done correctly, and that is our experiment in 2021. It's also it's a very strong quantum computational advantage claim. So. But after this early 2 first generation experiments, what challenges, there has been many development from classical simulation algorithm. And all those developments pose new challenges and opportunities to our following works. So let me just take you through these challenges. First, there are new classical algorithm that is specially designed for the threshold detectors in our experiment. So this means our first 2 generation experiment cannot resolve photon number information. And you can actually take advantage of this feature to design a better classical algorithm that can reduce the classical overhead from 2 billion years to just 70 days. So it's pretty amazing. And also, there are stronger mock-up distributions. So people design a better hypothesis of a classical version of the experiment, and which behaves actually quite close to our first generation of experiment. So this means we need to do a better experiment. And also, very interesting is people develop some mock-ups that can spoof our validation tools. So this means these distributions, they can actually perform better than ideal sampler. So this means our experiment is not a problem from experiment, but it's the validation tools itself need to have some improvements. So, and also there are some more technical results, means that they can exactly simulate certain information from our experiment. So this means we need to do our validation independent of such information. And with that, we recently released our 3rd generation experiment. There are many improvements. First is we developed a pseudo photon number resolving detection. So we can resolve photon number up to 8. And this can increase, this is address the first challenge I mentioned, and it can increase our quantum advantage by 6 order of magnitude when compared to the 2nd generation. So, and also, we improve our validation tools. The Bayesian test is now independent of those information that can be classical simulated. And also we use higher order correlation to exclude all existed classical mockups that are published so far. And this means this validation is the strongest in Boson sampling experiment so far. And we also do some kind of like Hamiltonian learning. So basically we realize that there are some noise in our experiment that can actually create a systematic bias between our experiment and our ground truth model. So we can learn such noise and actually build a better theoretical model of our experiment, which we can validate by Bayesian test is indeed more accurate. And with that, we are able to arrive at a 255 maximum photon number click number experiment. And this is 6 order of magnitude improvement over our previous Jiuzhang second, and also work from the Xanadu that also published last year. So another interesting question people usually ask is, can boson sampling have some applications? Well, for boson samplings, it's very hard, but for Gaussian boson samplings, there can be some applications. So that is because there are some mathematical correspondence between the Gaussian boson sampling setup to the graph problem. And actually, people have ideas to use this Gaussian boson sampling samples to accelerate certain classical algorithm to solve like dense subgraph problems and max-hub problems. And this is something we recently demonstrated, that we can use our device to accelerate this certain classical algorithm to improve their speed on solving these problems. And we observe an enhancement for up to 80 photon click events. And we also investigate their scaling behavior with problem size and also how they depend on the experimental noise. Yeah, so with that, I want to finally provide outlook based on this research. First, I think it's important to have a verifiable quantum computational advantage, because all our current validation tools have some limitations. They are either can be spoofed, or they can the classical overhead to calculate these validations are so hard, too huge. So this means we can either develop better theoretical tools to do validation, or we can maybe pick better problems. And also we need stronger experiment. This is the efficiency is mainly due to the efficiency. So there are some recent progress on how you can use limited efficiency to do better simulations. And we have some improvements over the time, but we still need to push further. And another higher level outlook is, can we achieve quantum speed up near term and practical use simultaneously? I mean, this is an open question for the whole field. And also we go back to the beginning of my talk. A violation of extended church Turing sets needs your experiment to be scalable. But so far, there are all noise in the experiment. So that means if we scale the experiment larger, the quantum advantage can actually decrease, because the noise becomes more dominant after certain regime. So that means maybe we need to turn to fault tolerant sometime. So with that, I'd like to acknowledge my mentor, Chaoyang Lu and Jianwei Pan, and also our collaborators around the world, and also to the amazing team that make this experiment possible. And that's all. Thank you.
Thanks a lot for that great talk. Are there any questions for Yu-Hao? Please, go ahead.
Thank you for the great talk. My question actually, I guess, corresponds to this picture here, that you have this beautiful optical setup to be able to do this many, many modes of sort of photons clicking together. Is there a notion for scaling orders of magnitude larger in terms of click count? At some point, it seems like the way it's being set up right now, you're just running into space limitations of mirrors and beam samplers and such. So can you comment on that? Yeah,
that's a great question. So I personally think it's not super hard to push to like thousands of photons. I think in this regime, we can have very, very strong quantum advantage. So for this quantum advantage experiment purpose, this scale has already, if go to 1,000 photons, that would be already pretty abundant. And if you want to go to, future applications like universal quantum computation, I think maybe you need better ideas on how to scale the system up.
Thanks for the great talk. Could you talk about how the resource requirements for the Gaussian boson sampling problem scale with loss errors? And is it different from the traditional boson sampling problem?
Yeah, it's a very good question. So let me begin with the traditional boson sampling. In that case, you need, like, say you want n photon in the front, you found n photon output. That means, if your efficiency is some value like eta, if you want n photon coincidence, your success probability is eta to the power of n. So that is an exponential decay with your efficiency and your photon number. In boson sampling, it's a very good question. So this year there is a paper from Liang's group which can say that if you actually have very large photon loss, there can be similar scaling, that your actual quantum resource for quantum advantage also decrease significantly. This is actually something I showed here. You can see that efficiency can decrease your effective squeezing a lot. And they just recently developed, I think it's an archive paper to use this to better simulate the experiment. And I think that's very good progress. And that's why, a higher efficiency is something we need to pursue it. I would say it's also like an exponential scaling.
Let's do one last question here.
We know that squeezing is quite fragile and sensitive to loss. How do you deal with that? Second question is, have you ever think about to change this into integrated circuits, like onto a chip or something?
Yeah. The first question, I guess I just also talked with his question, that it's very sensitive, and we need to push the efficiency much better in a future experiment. Currently, we have some ideas, and we're trying to do that. but there's still a lot of space to improve, I guess. For integrated photonics, it's a good question. I think the problem with integrated circuits is its efficiency is even lower than our phase space. So we don't have plan to transfer to that for this purpose of experiment. But I guess if you want to, back to like Adam's question, if you want to scale up to some quantum computation in the future, I guess integrated platform is something you can consider because it has better scaling, just in principle can be scaled up very easily. Yeah.
Okay, let's thank Yu-Hao again. Thanks.
Let's welcome our next speaker, Haocun from University of Vienna. We'll be talking about macroscopic quantum mechanics in gravitational wave detectors.
So thank you very much, and it's my great pleasure to give a talk here. And my talk will be focused on microscopic quantum mechanics in gravitational waves, and not just limited to gravitational wave detectors, but all fundamental measurements that can bring us new physics. So here is a background slide about the LIGO detector, and we know that gravitational waves has already been a booming field that even the 2017 Nobel Prize is given to this. So gravitational waves are actually the ripples of space and time themselves. And when it usually comes from the sources of two very large mass in the universe, such as black holes or the neutron stars. And when the gravitational waves propagate to the Earth, the whole space-time, including the whole Earth, got expanded or squashed. Which means if we build a very sensitive interferometer, and the interferometer can measure the difference of the two arms, and also the position of the mirrors, and at the same time it will tell us, okay, the gravitational waves are here. So here is a very simple scheme of the LIGO detector. Full name is Laser Interferometer Gravitational Wave Observatory. The idea is quite simple. It's a microsync interferometer enhanced by optical cavity. And what we are doing is we measure, as what I just said, we measure the difference of the two cavity arm or the two LIGO arms. What is very unique here is we have a large scale of this interferometer, and the test mass is quite big. So the suspended optics are 40 kilogram, and the arm length is 4 kilometers. That's also what makes this experiment so difficult. And we really made some progress. So here is a roadmap of what has been done, and also for the future, the LIGO detector, and also from 2017, Virgo also joined us, so we have a 3 detector organization, and the idea is in the future we can build a big network of the interferometer, gravitational wave interferometer network. So from the 2015, the observation run begins with O1, O here stands for the observing, and then 2020, I get involved in most of the O2 and the O3. So in the first observation run, what we found is a black hole merger. Well, in the second and the third one, what is more exciting is we saw these mergers of neutron star events. What tells us is that we can see something that can be collaborated with the astrophysicists, because the neutron star mergers will give us like gamma ray, X-ray, and all these are also important for building a network of the astrophysics and quantum physics, plus gravitational wave detection. So the gray area here actually is what we pause our observing, and we do commissioning and trying to improve the detectors. So we just know that the O4 just started this year. And here is a summary of all the gravitational wave detections with the first 3 observing run. And the x-axis is the cumulative time, y-axis is how many events that we can see. So you can see that from O2 and O3, there is a huge booming up. Like from O2, we can only see detections like several ones per year, but from O3, we can actually have detections almost every week. So what actually improves that detector that much is squeezed vacuum injection. So first, the question is why LIGO is suffering from quantum noise, or why quantum mechanics plays a role in such a big detector. The idea here is that because LIGO itself is an optomechanical system, that's the lasers interacting with mirrors, but at the same time, when you are trying to use light to measure something, there is a back action that the mirror is giving back to the laser light. And this is called quantum back action. And these two actions gives us a quantum noise that LIGO is suffering a lot. So there are several solutions that you can improve. The first one is definitely you can increase the power inside the LIGO because the more photons you are counting, the lower shot noise you will have. But at the same time, this is really a hard problem in LIGO that we have more than 300 of control loops. And every time when you change the laser power, we have to deal with all these things. So another smart idea is what I'm showing here is a squeeze vacuum injection, or we call it squeezing. The idea is, okay, we have a vacuum that is coupled into the interferometer, but vacuum is not nothing. We have the fundamental vacuum fluctuations, which brings this quantum noise in the phase quadrature. And what we do is that we use a squeezer, which is an optical parametric oscillator that I won't go into the technical details. But what it do is it squeeze and squeeze the vacuum so that we can dump some of the noise that we carry in the phase quadrature, but at the same time, we have to pay some expense that, sure, as the amplitude quadrature, we have a little bit more noise there. So here's a plot that's showing what it's actually doing. So the LIGO is suffering from the shot noise because we are detecting the photons. And after we inject in the squeezing, in the phase quadrature, the noise is squeezed lower and the signals appears up. So here is a plot with more ideas like how much we improve. The x-axis is the frequency, because in LIGO we analyze all the data, not time series, but the frequency domain. And the y-axis is the displacement, or it's telling us what's the displacement of the mirror that actually LIGO can detect. And this, for example, at 100 hertz, we can detect 2 times 10 to the 20 meters square per square root of hertz. And the light blue curve tells us, okay, how much. So actually, the lower the curve is, the more sensitive LIGO is. That's the basic idea this curve is telling us. And we can see that from the light blue curve, which is 02 to 03, which is the darker one, we are actually pushing the sensitivity to a factor of square root of 2. And this is from the 3.3 dB of squeezing. What is more interesting or exciting is that, okay, the squeezing is helping us or helping LIGO to detect more gravitational wave events, but at the same time, it gives us more physics or fundamental physics with, okay, in this large scale, think about what does it mean with 40 kilometer mirrors. We human beings are around 40, 50 kilograms, 60. So that's actually a really human scale system. So at higher frequency, the LIGO is suffering from shot noise. But at lower frequency, as what I said, when we do the squeezing, Heisenberg told us that we cannot buy this for free. So at lower frequency, which is the amplitude quadrature, we can actually see this quantum radiation pressure noise, which is the mirror that is giving back the quantum effect back into the laser light. And here is the important work that's done in 2020, that when we inject squeezing that is large enough, around 3 to 5 dB, we can really see that at low frequency, this quantum radiation pressure noise appears up. This is something that we are chasing for 20 years that we want to see in even smaller systems like milligram scale mirrors or microgram scale mirrors. And remember, this is in room temperature. So this is really something that we can see, okay, quantum correlations appears up, gives us quantum radiation pressure in LIGO system. So for a bit of future that LIGO is planning for, together with Europe, for the next generation of detectors, and this will include longer interferometers in different configurations. 10 kilometer and 40 kilometer Einstein telescope will be built in Europe as planned. And Cosmic Explorer we will put in cryogenic with heavier mirrors, longer arms as next generation of LIGO. And all these really need more quantum techniques and better solution of how we solve this quantum problems. So expansion is currently I'm in Vienna, and what I'm doing is, okay, the quantum techniques is helping LIGO a lot, but quantum photonic experiment can also help us to discover some fundamental physics question. And one of the questions we want to solve here is how does quantum interact with gravity? Because we know that quantum is more served for smaller scale systems, but gravity is more on the larger scale, and it's really a fundamental question. Okay, how they interact with each other? Is a gravitational wave, gravitational field quantized, or they are more separate? But we are still far from the theory, like concrete theory for an experiment. So our idea is we are trying to put quantum phenomenon into gravity fields. And the prototype experiment here is we built a quite large interferometer, again a SENIAC one, but this time we built into fiber. And the advantage that we use fiber is with fibers you can spool the fibers put the fibers into a spool. And with 40 kilometer fiber, you can really put your experiment into the lab instead of like LIGO, you have to have a large space. Right, so we have 750 SENIAC quantum interferometer, and we inject entangled photon inside it. And what we can see is instead of facing only one phi with an interferometer, we can actually scaling up this phi into, with 2002 entangled states, we can scale up to 2, and in the future, we can put more entangled photons to, so what I see is that LIGO, we have the signal that we cannot control because we cannot control black holes. So we can dump the noise by using quantum techniques, and the signals appears up. And what we are doing here is we can control actually the signal because we use entangled photons to double up the signals, and we can increase the measurements. So basically, here is a closing remarks or a summary of my talk is, so definitely quantum enhanced advanced LIGO is already there, and it helps us to increase the detection rates by several times. And then the microscopic quantum mechanics is very important. We saw with 40 kilometer mirrors, with 40 kilogram mirrors and 200 kilowatts laser light, we see this quantum mechanics, quantum radiation pressure, and correlations. And all these quantum technologies should be used for future gravitational wave detection and also fundamental measurements to discover new physics. Thank you very much. Yeah, so for this experiment, actually, there are noises, but the point is we are using SENIAC, which means lights are going through the same path. So there is a large amount of noise are dumped by the common mode. But in the future, we are trying to build a Mach Zehnder. In that way, we are suffering from noise. And we have to do, so the idea is, first we need active stabilization for so this project is also collaborative with LIGO, with all the experiences of dumping the seismic noise and the environmental noises. And then there will be active fiber noise, because when light traveling through the fiber, it will induce some noise by itself. So there's a technique called Doppler noise cancellation that we will do for this. Cryogenic can be done with, well, it's easier with smaller experiment, but for LIGO, cryogenic is already on the plan. For this fiber one, we don't have it yet. Yeah.
Thank you for the talk. I'm seeing that you made mention of room temperature and different ratings for the mirror and the laser. Now we are seeing the near future if this becomes feasible. Did you ever try changing the temperature conditions, and what do you think can be done to help when we have winter session or cold weather session? Did you ever try anything like that? or if you have any perspective you can share with us. Thank you.
Yeah, I think this is related to the last question, I think it will be reasonable to put everything into cryogenic. The problem is with cryogenic, there are lots of technical and mechanical issues that we need to solve. And with everyone who use crash stats, probably you know that once you have this cryogenic on, then there are lots of vibrations. So we need to have another system with active stabilization for the cryogenic itself. At the same time, there must be some connection between your cooler and the mirror itself. And because the LIGO mirror is suspended, so we have to suspend the mirror, but at the same time connect it to the cryogenic and to deal with all these vibrations. But definitely, yes, with lower temperature, the noise should go down.
Have you estimated the actual sensitivity of your fiber gyro, and how do you null out essentially the vibrations in the lab that are going to leak into your measurements? And do you have an estimate for the deadband of your sensor? Yeah, so currently, actually, this work we have just done, and we can reach the micro-radians sensitivity. That's currently the level. And that helps us to reach the Earth's rotation. So we can measure the Earth's rotation with this Sagnac interferometer. And the next target is we want to measure gravitational redshift with a similar setup. So yes, and then I think we are tending to go another 6 to 9 orders of sensitivity with all the, so micro times 10 to the -6. That's a number. When you say deadband, you mean frequency or? Right, so with this experiment, it's actually different from LIGO, because LIGO is, we have a frequency band, but this one is actually a DC measurement. Another idea is, because it's really hard to manipulate the gravitational redshift is always there. The only thing we can do is whether we do modulation between the two light, or, but the current idea is we do a DC measurement. Then, yeah, the low frequency noise we have to deal with very carefully. Or we have all these noises squash it into a very narrow band peaks so that it doesn't disturb our DC measurement. Yeah.
Maybe a final question.
Very short question. Is there an estimate for how long it would take a 40-kilogram suspended mirror to cool down and reach base temperature?
Okay, good question. And that actually also depends on how much temperature you want to reach. So for LIGO, I think the cryogenic is not same or even in a similar scale that people are doing like superconducting is. We are not achieving millikelvin. So currently the two setups are one for around 100K. The other is only 20K. Then that means, well, for LIGO, the thing is even for vacuum, we took a long time, and that can be done at the same time. So several weeks, half a month. That's a simple idea. Yeah.
Let's thank the speaker again.
All right. Next up is Freek Witteveen, who is a postdoc at the University of Copenhagen, and he will tell us about mathematical methods for tensor networks. Stage is yours.
All right. Well, it's fantastic to be able to speak here. I will, so thanks a lot to the organizers. I will tell a little bit about some work that we've done in collaboration with people from Copenhagen, Amsterdam, Bochum, and Madrid. And it's about mathematical methods for tensor networks. So what I will do is I will first take some time to, well, first I will give some motivation. That's maybe not even completely necessary for this audience, but then I will take some time to explain what is a tensor network. And then in these last two sections, I will briefly say something about these sort of mathematical works that we did in this direction. So yeah, let's get started. So what are we interested in? Well, we're interested in understanding quantum many-body physics, and I don't think I have to say here why this is interesting. I mean, there are many phenomena in nature where we have sort of correlated but large systems where quantum mechanics plays a big role. And you know, to get really basic, we know that at quantum mechanics it's about on the simplest level, the simplest system is just a qubit or a spin where we have a particle that can be, let's say, up or down, and it can be in a superposition of these two states. But then in a many-particle system, so in many-body physics, we have a lot of particles, and they can all be in like either up or down. Let's say that we have some two-dimensional spin system, some sort of quantum magnet, and then we see that the quantum state is described by a superposition of all these possible configurations, right? So this is the formula. And it's a superposition of all possible spin configurations, and that means in particular that the wave function, the state, has an exponential number of parameters. And well, an exponential number grows very quickly, so we see that if we, for instance, want to simulate this on a classical computer, already just storing the wave function in memory is too large for moderate system sizes. So, right, this was one of the original motivations for doing quantum computation, that a quantum computer should be able to store the state in memory, and that's nice. However, this is not the full story, because in fact, most states that you will ever encounter in sort of real life or in real theory, actually, so that the states that we care about, they actually will have some additional structure, and they may have an efficient description. So maybe they don't need all of these exponentially many parameters, and there's some more efficient description of them. So a first clear example are actually states that are prepared by a quantum computer, in which case, if we have a polynomial number of gates that prepares a certain state, then that's just these gates, which each only have a few parameters, gives me a nice efficient description of the states, right? But there's another important class of states which I care about for this talk, which are states that occur in many-body physics, which are ground states of local Hamiltonians. So in that case, if we again think of, let's say, a spin system, then typically the Hamiltonian that describes the system will have local interaction. So it's not just it's an operator which is written as a sum of local interactions, and so we can think again of this 2D lattice. And then we want to understand the ground state, so the state with the lowest energy. And this ground state turns out in sort of practice to have a nice property, and this can be understood by looking at dividing the system into two parts. We call them A and B in this picture here. And now look at the correlation that the state has between these two parts. And if the state was just like some generic state, I just randomly picked all those exponential coefficients, then what you would find is that the amount of correlation typically just scales with the size of the system A. But in ground state physics, what we typically find is that the amount of correlation actually scales with the size of the boundary between A and B. And there's something intuitive to this, because the interactions, right, they're only sort of across the boundary of the system, so that it makes sense that somehow the correlations also have some local nature. But this is actually a quite deep question how this works precisely. It's not completely understood, both mathematically and on a physics level, I would say. And this phenomenon is known as an area law. So the message of this part is that what we see is that ground states of local Hamiltonians, they somehow have local correlations, and we could hope maybe for some efficient description here, because these correlations are local and not global. All right, so now I will tell you a little bit about what is a tensor network. And so first of all, what is a tensor? Well, a tensor is just a collection of numbers which is labeled by some indices. So if there's two indices, then it's just a matrix, and if there's more indices, then it's a k-tensor if it's k indices. And for the purpose of these tensor networks, we will describe them as a blob with a number of legs that corresponds to the number of indices that there are, and sort of label them according to these indices. And then a key operation is the notion of contraction of tensors, where you take two tensors, and if they and you draw a link between the two blobs, so you connect two of the legs, and that means that you're gonna sum over the index that you've contracted, so the one that you've connected, right? And that gives me, so here I start with a 2 tensor and a 3 tensor, and then the contracted one, it has sort of 3 dangling legs left, so the resulting object is a 3 tensor. A tensor network now is just the general idea of starting with a collection of tensors and contracting them according to some graph, and that leaves us with some final tensor. And then, you know, a tensor is also just the same as a, right? It's the same as a quantum state on a number of parties that corresponds to these dangling legs. So these dangling legs, the one that remain, they represent a quantum state. All right, so yeah. So let's look at a couple of examples. So the first example is a very simple example that we hopefully all know and love, which are matrices, right? Which are just 2 tensors. And in that case, we see that if we contract one of the legs, that is just the same as matrix multiplication. So the whole thing of tensor network contraction, it's just a generalization of matrix multiplication. Right, and here's another example. If we now also contract these other legs, then we compute the trace of the product of the matrices that you can easily verify. So a second very important example, and we actually already saw it in the, or it was mentioned in the talk by Adam, and now I can actually explain a little bit what it is, are so-called matrix product states. It doesn't really matter why it's called that, and they were invented in the 90s, and they have found a lot of application in many body physics and beyond. And here we have sort of 3 tensors where sort of two of them have a dimension which is called the bond dimension, and one is the physical dimension, and we contract them according to this structure here. And that gives me a quantum state on n copies of this physical Hilbert space. And the nice, or one of the great features, so they have many great features actually. So one of the great features is that they give a very accurate description of one-dimensional ground states. You can prove this rigorously, but also in practice it just works really well. And in Adam's talk, we actually saw that they were used to simulate time evolution, which is a slightly different problem. And actually, they're kind of bad for this problem, but even there, they still work well. So, and for ground state physics, they work even better. So they're very nice. Then, but the problem is that they only work well essentially in one spatial dimension. And one spatial dimension, it's not as we also want to understand higher spatial dimensions, of course. And the generalization to higher spatial dimensions is known as projected entangled pair states, or PEPs. And here we just do the same thing, but now we do this on a 2-dimensional lattice. Okay, so this is the very same construction. We contract this on a 2-dimensional lattice. And an important feature of this is that by construction, it is not very hard to see that because the way you set it up, these correlations satisfy an area law. So, so in that sense, it might be a natural ansatz for ground states on 2D lattices, and it turns out to be the case. So there is actually a difference between states that have this area law and states that are of this tensor network form, but for practical purposes, these are a very good ansatz. So they seem to be a good approximation to quantum ground states. And they are both useful sort of in theory and numerics. So one thing you can use them for is to sort of reason theoretically about ground states. And you can, we also see that they are, in many cases, they are actually the exactly solvable models which have perhaps ground states, and we can use this to understand topological phases or symmetry protected topological phases. And on the other hand, you could also sort of, for instance, do a variational optimization over this class of states and use that for numerical simulation, right? Because now we see that we have, if you look at this object, it has a polynomial number of parameters, so it's reasonable to do a variational optimization over it. Okay, so example number 4 is quantum circuits. So they actually also have a direct interpretation as a tensor network, because I can just interpret each of the gates as a tensor itself, and sort of evaluating the circuit now is exactly the same as contracting the tensor network. And this has been used for classical simulation of quantum computers to quite some effect, as in the talk of Adam, and also many of these supremacy experiments have in fact been simulated by tensor network experiments. So I think there's this sort of back and forth where people come up with nice experiments and then people simulate them with tensor network methods, so that's quite nice. Yeah. All right. So now I want to tell you a little bit about, where sort of we come in this, and which is sort of the mathematical theory of these things. So linear algebra is something very nice. We all learn it in our first year of physics or math or computer science. It's very well understood. It has lots of nice theorems. You can diagonalize matrices. There are efficient numerical methods that you can run on your computer. And tensor networks are quite different. They are using multilinear algebra, and it's much harder. So it means that many theorems that you would like to think about, maybe they just are very difficult to understand, or they don't even exist, and numerical methods tend to be inefficient. So for MPS, it's a little bit different. They actually do have nice theorems and efficient numerics, but for these two-dimensional PEPs, for example, this is much more complicated. So we have done some work in this direction. So one thing that we looked at is that there is an important aspect of symmetry in these tensor networks, where if you insert invertible matrices on the tensors, then you see that if you contract, they cancel each other. So it means that the tensor, I can sort of change the tensor and I get the same quantum state. And we would like to sort of fix this redundancy, because this leads to numerical instabilities. And there are also sort of good theoretical reasons for fixing this, this redundancy. And so for PEPs, we propose some particular sort of canonical form where you sort of choose a specific tensor where you fix this gauge degree of freedom. And whereas for MPS, sort of these canonical forms were already very well studied and well known. For PEPs, I think there was no sort of rigorously defined good canonical form. There were numerical recipes, but we show that this one has sort of particularly nice properties. If you want to know more about it, please come to me in the break and I'll tell you more about it. So a second domain in which we try to extend the mathematical theory of PEPs is by connecting it to something known as algebraic complexity theory. So the big problem of these PEPs tensor networks is that they are numerically not efficient, and you can actually prove that computing with them is sharply hard, which is very hard. So yeah, so that's a big problem, and in practice you have to resort to approximations. And to better understand the complexity theory of these tensor networks, we look at a generalization where we allow different contraction rules. For example, where you sum over 3 indices instead of just 2. And this kind of corresponds to replacing bipartite entanglement in your network by multipartite entanglement in a there's like a precise formulation of this. And we try to sort of compare these different entanglement structures or these different contraction rules. And the motivation for this is that actually if we look at this very simple example, so the contraction rule that I just showed versus sort of like the standard one, then this understanding the relation between these two things is equivalent to understanding the complexity of matrix multiplications. And this has been studied extensively in the past, and this is clearly a very interesting problem for computer scientists and theoreticians, and we've tried to import some of the techniques that are developed in that field to tensor networks as well. And right, so I think there are sort of a lot of open questions here still, but we've sort of made some attempt to import some of those techniques, which are based on sophisticated algebraic geometry and sort of mathematics of the theory of tensors. All right, so in conclusion, so tensor networks are a very nice tool, I think, that are on the interface between math, computer science, and quantum physics. And I think there is a lot of, so they're useful for numerics, they're useful for for theoretical physics, but I think it's also a very interesting area for mathematicians to improve the theoretical tools.
Thanks a lot, Franck. Very nice talk. Any questions? Go for it. Actually, there's one. Yeah, go ahead.
So you mentioned this minimal canonical form. How hard is it to calculate it in general?
That's a great question. Thanks a lot. So yeah, so actually, I didn't have time to mention it, but now that you ask it, I can fortunately talk about it. So here, this minimal canonical form, I kind of flashed it a little bit quickly. So it's phrased as a minimization problem. So it's not obvious that you can actually compute it, and it could be a hard computational problem, but actually recent progress in sort of the theory of optimization over non-commutative groups has shown that you can kind of do gradient descent on these groups, and you can actually find this object in reasonably efficiently. So it is computable.
Yeah, thank you for the nice talk. Could you comment, so you show here sort of like a square lattice PEPS type pattern. Can you comment on sort of how these different theorems that you develop are generalizable to sort of arbitrary lattices of these tensor networks? And yeah, so I guess in similar ways, the last question, how computable these things are for different arbitrary lattices?
Yeah, that's also a very good question. So in this particular case, it's something we haven't, so for this canonical form, we haven't explored it super deeply, but there is some so this case is for a translation invariant situation. So if you go to arbitrary lattices and have non-translation invariant tensors, then there is a general framework that allows you to use these sort of group actions and define similar canonical forms, but maybe it's a little bit less clear what they mean or how useful they are.
Do you have some sort of renormalization theory for this, that you can basically coarse grain the tensor contraction and becomes an effective tensor?
That's a very good question. So I have not worked on this specifically, but there's a whole sort of field of something called tensor network renormalization, indeed, where this is precisely what you do, where you start with sort of a big tensor network, and you coarse grain, and at the same time you kind of like you make the bond dimension smaller as you go, and then you converge to some fixed point, and that fixed point is going to be related to the CFT of the corresponding fixed point of the renormalization group. So that is something that has been studied, but I do not know how to relate it to this particular thing.
So you showed that there's possibly a benefit if you consider multipartite entanglement compared with bipartite entanglement. For the multipartite entanglement, does it kind of matter how many coefficients or how many states are participating in that entanglement? Or like if I have like a 3-body, is that better than 2-body? Or is there some number scaling related to the multipartite entanglement?
I think there is no general thing you can say, and I think that's also not it's a little bit subtle whether or not there are sort of actually advantages of doing this, I think. So I think at this point it's kind of like a nice mathematical theory, and I think we're able to say some interesting things about it, but it's not so clear what advantage exactly means. But I think there could be interesting computational advantages, but like it's certainly, like if you want to look at that, then you certainly have to go beyond 2 parties, and the sort of the notion of entanglement that we look at is under SLOCC, if that's, I guess that makes sense. And then somehow what's kind of nice is that in the tensor network setting, the SLOCC framework is kind of the natural setting for what entanglement means. So yeah, I don't know if that answers your question, but
we can talk about it more.
Yeah.
Okay, let's thank Freek again.
Please welcome our final speaker, Anjun from CU Boulder, will be telling us about simulation of BCS superconductors in cavity QED systems.
Okay, good afternoon. My name is Anjun. So first, I would like to thank the Boeing company and the Chicago Quantum Exchange. It is a great honor for me to be recognized by the Quantum Creator Prize. So today, I'm going to tell you recent projects I'm working on. This is collaborating with the experimental group of James Thompson at GILA. So we are working on the simulation of BCS superconductors in cavity QED systems. So before we get into the details of our research, so first I would like to briefly introduce the BCS theory. So this is proposed by Bardeen, Cooper, and Schrieffer in the 1950s. And the key idea is that when there is two electrons moving in the crystal, and they can couple to the phonormal, the vibration in the crystal, and forming an effective attraction interaction between these two electrons. And this attractive interaction would make these two electrons forming Cooper pair. And in low temperature, so there is a microscopic number of Cooper pairs that condense each other, so that when you have electric field, they're all moving together, and then this can explain the phenomena of superconductivity. So BCS theory actually can apply to a wide range of fields in physics. And of course, it can apply to superconductors that the Cooper pairs are formed by electrons. It can also apply to electrical fermions, when the Cooper pairs are formed by neutral atoms. You can also explain the QCT matters, the scalar superconducting phase, where the Cooper pairs are formed by quarks. So understanding this BCS theory of course, can benefit a wide range of fields in physics. So here we are focusing on the out of equilibrium physics of the BCS superconductors. So unlike the equilibrium phenomena we usually see, the exploration of this far from equilibrium physics are limited by experimental controllability. So the typical experiment in real material is called the Terrace-Prumpo experiments. And these type of experiments, it is hard to actually reaching a clean comparison between the theory and experiment on this far from equilibrium physics. People also considering doing it in fermionic superfluids. And while the techniques using to quench the interaction is the Felix-Bloch resonance, it also have inevitable heating effects. So this is the reason why we think that if we can do quantum simulation in spin systems, we can have more insights on this far from equilibrium physics. So the idea for quantum simulation in spin system is we need all-to-all interaction to simulate the BCS superconductors. So one candidate is using the cavity QED systems. This is a system that when we have an ensemble atom actually trapped inside the cavity, and these atoms can talk to the cavity mode. Actually, it is light field actually bouncing between the two cavity mirror. And so that each atom actually can talk to the same light field and then have all-to-all interaction between them. Another example is the dilute ensemble in a harmonic trap. And here we will focusing on these cavity QED systems. So here I first would like to show you is the Hamiltonian, the BCS model. The first term is describing the kinetic energy of the electrons. And the second term is describing the scattering of the Cooper pairs. So Bardeen, Cooper, and Schrieffer points out that the most important term in this interaction is, you can understand, is the electrons with opposite momentum, they're forming Cooper pairs. And the interaction process is that the Cooper pairs in one momentum, they are scattered to another momentum. And they also describe the superconductivity by the order, using a parameter called the order parameter. So it has a physical meaning is that when the system actually enters the superconducting phase, you can find an energy gap proportional to this order parameter in the system. So later, Anderson points out that we can also understand this BCS model in spin systems. The idea is that I can map a Cooper pair, so with electrons in momentum k and minus k, and I can map it to a spin up particle in momentum k. And I can also map the absence of Cooper pair into a spin down particle in momentum k. And in this case, I can rewrite my Hamiltonian in terms of spin operators. So the first term is now become a disorder in the frequency of the spins. And the second term, originally describing is the scattering of Cooper pairs from one momentum to the other, we can now understand as spin exchange interactions, where spin up particle in momentum k prime is flipping from up to down, while another particle in momentum k is flipping from down to up. We can also understand the BCS order parameter as the overall coherence of all the spins. So now what I would like to discuss is the out of equilibrium physics, or here we're showing is the dynamical phases in the Schubert conductors. So the idea of dynamical phase is that when we're starting from the ground state of the system, described by the Hamiltonian H initial. So in this case, we have the order parameter delta BCS initial. And then we perform a sudden quench the system so that we kick the system out of equilibrium. So the Hamiltonian now is governed by the Hamiltonian final, but because we are doing suddenly, so that the BCS order parameter still remains for the initial value, so it is not equal to the equilibrium value of H final. So this will lead to dynamics in the BCS order parameter. And we can see distinct dynamical behavior depending on how we quench the system. So there is 3 types of dynamical phases we can find in this quench experiment. This depends on the ratio between the initial BCS order parameter and the equilibrium value. And the first, we call it phase 1, is described by the BCS order parameter quickly decay to 0. While phase 2 is, instead of decay to 0, the BCS order parameter will saturate to a finite value. And the small wiggles of them oscillation there is the excitation of the Higgs mode. And the phase 3 is described by the permanent oscillation of the BCS order parameter. And for these 3 dynamical phases, the phase 1 and phase 2 are already observed, while the phase 3 actually is never observed before. So our goal is to observe all these dynamical phases in our experiment. So now I would like to introduce how we implement this BCS model in cavity QED system. So first, I would like to introduce is the spins exchange in action term. So we engineering wire cavity mediated interactions. So here we are using is the strontium-88 atoms, features a narrow transition between 1s0 to 3p1 state. And we define the 1s0 state as the spin down and 3p1 state as spin up. And so the atom light in action in this case can be described by the Tavis-Common Hamiltonian. And here we use A to determine the cavity field operator. So the first term in the Hamiltonian is describing there is a frequency detuning between the atomic transition and the cavity. And the second term is the atom light coupling. Just means that when an atom absorbs a cavity photon, it can go from spin down state to spin up state. So because the cavity resonance is far detuned from the atomic transition, so we are considering the cavity field is adiabatically following the atomic dynamics. So in this case, we are finding that the cavity field is proportional to the BCS order parameter in the model. So this gives us a very efficient way to measure the order parameter. It's just by measuring the light leaking out of the cavity, and we can have a real-time tracking of the BCS order parameter. And we can also understand this spin exchange in action in this case. So when we plug in this adiabatic following dynamic cavity field into the Hamiltonian, we will get is exactly getting back to the spin exchange term in the BCS model with the coefficient chi equal to g squared over delta c. And in this case, we understand is when a particle going from spin up to spin down, emitting a photon to the cavity, and this photon can be reabsorbed by another atom going from spin down to spin up. So this can explain why there is a spin exchange in action. And now I would like to explain is the kinetic energy of the electrons, and then we implement this term using AC stack shift. So the idea is that we using a laser to resonantly couple the spin down state to another state in strontium atoms, and then we have a beam shaping so that actually each atom can fuse a different AC stack shift. So to actually making the fermionic systems, so here I would like to first tell you actually what is the BCS ground state looks like. So for the states actually is below the Fermi level. Here it's called KF here. We will have actually most of the states actually is occupied by fermions. So we can considering a spin model is actually there is spin actually pointing to the upward direction. So we consider this part as a large spin. And then for the states actually above the Fermi level, because they're mostly actually unoccupied. And so equivalent is that their spins are mostly pointing to the downward direction. So we consider this part is another large spin. So to mimic the fermionic system, so we can use two atomic ensembles in the cavity. So the one ensemble is representing the states that is below the Fermi level, and the another ensemble is representing the states that above the Fermi level. And we can engineer there is a frequency spreading of each ensemble. We call it E sub W. And there is an energy splitting delta S between these two ensembles. We call it delta S. So with all these tunabilities, we can have a phase diagram. In this case, the tunability in this case would be the ratio of the chi n over E sub W. N is the atom number, so the chi n means the interaction term. So we can have this tunable ratio of chi n over E sub W, and we also have the tuning is the delta S over E sub W. And then we can see that in this phase diagram, we have three different dynamical phases. So now I would like to go to is the experimental observation. So first is the phase 1 to phase 2 transition. So in this case, what we do is we vary the ratio of chi n over E sub W. So what we do is we first using a pi-half pulse to the system so that to prepare the state is equivalent to the ground state when the interaction is large. Then we turn on the frequency spreading E sub W so that we quench this ratio to a finite value. So what we see is that for small value of chi n, we are in phase 1 so that the BCS order parameter quickly decay to 0. While for the large chi n value, what we see is that the decay speed will be becoming slower. Here I explain that why they are not saturated to a finite value is that because there is still dissipative process in the cavity. For example, our atoms inside the state, they can have spontaneous emission. So this will lead to the BCS order parameter will not saturate the finite value. They will eventually decay. But you can clearly see that there is a large separation of decay timescale between these two phases. And also I'd like to point out is that the small wiggles actually you can see in the initial oscillation. These are related to the Higgs oscillation. Now I would like to go to is the experimental observation for the phase 2 to phase 3 transition. So in this case, instead of varying the interaction strength, what we now varying is the energy splitting between the two ensemble delta S. So for small delta S, we are actually in the phase 2 where we will see is the damping of oscillation. So you can see that actually in the top two curves, you can see that the oscillation damp quickly. And while when we go into phase 3, you can see that in the experiment, we can see the oscillation damp much slower. So this marks the first demonstration of phase 3 in experiment. Although I need to point out that there is also dissipation process when this oscillation goes forever. And another point is that there is still some discrepancy between the theory experiment. This might due to there is also some process in experiment like the excitation of axial sideband that we are not fully capturing in the theory model. So apart from, last slide. Apart from the conventional superconductors, so our protocol actually in principle can generalize to unconventional superconductors, for example, the topological superconductors. So this time with topological superconductors, it features a transition with a change of winding number, and this can exist for both equilibrium and non-equilibrium. So the way to implement in cavity QED system is that we can map these momentum states into real space lattice sites, so that actually the atoms at their position, actually they can couple differently to the cavity field. So with a given amplitude and phase, actually we can mimic this P plus IP Hamiltonian, where the spins exchange interaction actually can depend on their momentum state. So this idea can also generalize to D plus ID superconductors and may also competing superconducting orders. And we are working toward this direction. So at the end of my talk, I would like to thank my advisor, Anna Maria, and the theory collaborators, Robert, Diego, David, and the experimental collaborators in James Thompson's group. Thank you for the funding support, and so thank you for your attention.
Questions? I have one, actually.
All right. While they're passing the mic, you mentioned this very intriguing P plus IP phase. Can you comment on whether you could expect to see even these Majorana fermions appear if you excite the P plus IP?
Actually, in this case, we need a different design to actually seeing the Majorana fermion, because the Majorana fermion actually happen at the boundary. But here, what we're simulating is the momentum states of the system, so that it should be actually equivalent to actually the bulk physics of P plus IP. So if we want to implement a boundary, actually we are thinking of this by adding actual coupling, so that it mimicking there is a boundary in the system.
Thanks for a very nice talk. So in your fermionic kinetic energy, you had this delta S term that looked very different than like a fermionic metal. It looked like you had a gap, right, in your normal system. So can you comment if that's, like, whether this is a good analogy to a metal with like a pairing interaction, or is this some sort of two-band system, like with a little bit of a gap there?
Yeah, this is a good question. So actually, our originally thinking to actually introduce this gap is just a trick to seeing phase 3, because this is the most easiest way in experiment to trying to see this the permanent oscillation phase. But actually, in principle, the phase 3 is not necessary to actually need a gap to see it. I'm not sure if I can get to the backup slide. Maybe I can find it. Yeah, so here is another scheme showing that if we can first introduce a gap in the system, but we remove it later, and we can also see that the permanent oscillation behavior they're still there. So I would say is that this phase 3 physics is not required that there is a gap there. And for your another question is that we noticed that there is a connection to this two-band model, but we are currently not thinking very carefully how is the actual connection, or what would be the difference in the dynamics.
Thank you.
Thanks for the great talk. I was wondering, in your Hamiltonian, like you have this chi term, does the atom seize different fields that could cause some like disorder in your chi, and whether that influences your results?
Oh yeah, so this is a good question. So maybe let me see if I can go back there. Yeah, this one is also fine. So here our assumption is always that the chi term would be the same for all the atoms. So if we are considering the case that when the chi term is coupling differently to different atoms, for example, you can see that this P plus IV Hamiltonian, for different atoms, for example, in different momentum, they're coupling differently. So if you're considering that they are coupled differently, we can, in principle, can simulate more interesting physics, such as these topological superconductors, and they would thus change the dynamics. But another point I want to comment is that if you just want to see the phase 1, phase 2, and phase 3 as these dynamical phases, they also exist in this when you have different coupling of chi.
Maybe I can ask a final question. How does the all-to-all interaction of the spin exchange, how critical is that to the simulation of the BCS superconductor? And are there analogs to systems that have spin exchange interactions but are not all-to-all, for instance, falling off with power law decay or something?
Yeah, so I would say is that I am not sure. So there is system, for example, like dipole interacting system, they also have this spin exchange interaction. But I'm just not sure there is a direct connection to this physics of BCS model. But I could say is that in this system, at least you are still able to see the dynamical phases. For example, the phase 1 to phase 2 transition. So when you have this stronger interaction, you can see that you can keep your coherence for longer. And when you have slow interaction, you can see the coherence decay faster. I think this can also see when you have power law interaction.
Yeah. All right, thank you.
Okay, thanks to all of the speakers for these very nice talks. We move on to the panel section. So I would like to welcome all the speakers to the stage. And I would like to open this up to the audience, if there are any questions for the panel. People are maybe thinking about this still. I can start off with one. So we've heard in the talks that demonstrating quantum advantage always has two elements. You have the experiment, and then you need to make sure that somehow classical computers are bad at this or struggle with this in some way, right? And what I find very fascinating is that in the theory sector, these quantum advantage experiments have actually spurred a lot of interesting research, where we now have improved simulation techniques using tensor networks, or we have these quantum-inspired but classical algorithms for recommendation systems, for example. That was a big result. And so I would love to hear your opinion on the tension between the two things, whether there is a tension. How do you think about this, and do you think the two sides could actually benefit from each other? If that question makes sense.
Yeah, maybe I'll start and just say that I think that there definitely is a tension between the two. I think that the sort of push and pull between classical and quantum is something that will probably be going on for a number of years until sort of true fault-tolerant thousands of logical qubits quantum computers exist. And I do think it really pushes both sides forward. So, for instance, in my experiment, we sort of had to develop a new type of doing these tensor network methods that was really highly tailored towards our specific system in order to do these simulations more efficiently. And now that we've done that, we sort of have this tool for doing also simulations of dynamics for not just sort of the quenches that I talked about, but for physics where we're looking at ground states, where we're looking at sort of more dynamical quantities of interest. So I think that definitely we do learn about both sides from it. And I think that, yeah, until there's like a real large-scale quantum computer, there's inevitably going to be this tension, because I think at the end of the day, quantum computers are noisy and probabilistic, and once you allow a classical computer to also be noisy and probabilistic, they become extremely powerful in a lot of different arenas. So it's definitely a challenge to sort of find the problems in the near term where we can find those benefits.
Yeah, so for me, I think I personally really appreciate this research from the classical simulations to following our work. Actually, after our publication of our early papers, there are many theories reaching us and discussing, is there any possibility to improve on the classical simulations with us? And we understand a lot, and we get a lot of insights into what quantum advantage actually means, and what can we say about such experiments. So I mean, I would say this as early signs of value created by quantum processor experiments, because it can provide a lot of new insights into the quantum physics itself. And this is something, if you don't do these experiments, people don't even think about it. And yeah, and I think this will continue for quite a few years, and that's, I believe, how early computers can benefit the community. I mean, if I set a quote from, Donald Knuth, is the best theory is inspired by practice, and the best practice is inspired by theory. I think this is very good currently we are in a good time between the theory and experimenting in quantum physics. I mean, this is not exist in all fields of physics. Some fields, the theory and experiment has a huge gap, but in quantum physics, the complexity experiments, it's a good stage. And I personally also like to discuss with the theorists on simulation.
Well, I think for me, it's more fundamental system is including the optomechanical system. And in the specific, when light interacts with matter, what we care more, we usually don't use a term of quantum advantage, but we say, okay, we want to beat the standard quantum limit. And the standard quantum limit in optomechanics is not one factor, but it also depends on different frequency. And this has already been achieved by current LIGO after squeezing. And then the question would be, okay, then how much we can beat? Is there a even more fundamental limit? That's how far we can go. And another question that I'm interested in, okay, now we have one detector, one system, and here is a limit of that. If we use distributed squeezing, or if you use distributed quantum methods, whether there is another quantum limit for multi-system. And are there some ways like to be that? This is a specific question. And definitely using photons, say, measure gravity effects or gravitational effects, the quantum advantage is something that we focus a lot on. And I do want to have maybe a discussion or another question for you two guys is, because we have all these losses when dealing with photons and light, do you think these losses will be will hurt the quantum advantage, and maybe in some level, say, if you have too much loss, then we will never see quantum advantage anymore?
Yeah, I think this question is for me. So I guess the loss is indeed an issue that we just realized recently, in maybe discussion with Liang's group. With very recent results, they discovered some tensor network approximate sampling algorithm to take advantage of this loss and to better simulate the experiment. And I guess they also significantly reduce the overhead. So I think this, this provides motivation for the experimentalist to further improve on our efficiency. And the efficiency of photonics processor is important itself in terms of, if you want to scale up for universal quantum computation. So I think this is indeed a challenge and opportunity.
Can I ask a quick follow-up to your answer before we go on, actually? So you talked about like these next generation LIGO experiments that are coming online, LIGO and Virgo experiments that are coming online. Do you sort of have some sense about, I guess, how much more important it is to push on the quantum side of increasing the squeezing, et cetera, versus how important it is to just make a bigger detector and sort of push on the classical side of these systems? Is there some sense of which gives you the more, I guess, bang for your buck, your grad student hours, et cetera?
That's true. Actually, that's always a question that I also ask myself. I think in terms of the gravitational wave detector and also particle physics, because we also discussed with dark matter with quantum methods a long time, and these kind of projects, they have their own natural property that we have to have longer plan. Like LIGO or CERN, that everything is planned in 20 years or 40 years. And there are many techniques that when we plan to do something, the techniques are actually not already there. But then we have to, but that doesn't mean anything is stopping us, but we have to solve all these techniques first. Like what I'm doing at MIT is we cannot do all the physics and the experiment with the 4 kilometer directly. So we grab the physics out and bring that into a small lab. And to explore all these physics and lab stuff at first, say squeezing, we build a squeezer that is qualified to use in LIGO first. So these involved in, with all these generation of students, they also, because we also care about students' career, that they also discover new physics and publish papers, but at the same time, these kind of techniques can be used into a larger detector. With the long-term experiments, definitely yes. And then the question comes, what is physics? I think solving technical problem and mechanical problem itself is also part of the physics. So that's something we have to face and deal with. They are not that contradict. Yeah.
So I guess the question was about the synergy between like classical simulation trying to keep up maybe with sort of quantum advantage potentially, and I think there's a lot of synergy. And originally, I would write like the whole idea of quantum computation is kind of quantum physics inspiring computation to a new paradigm, and I think that in some sense the whole effort to develop the quantum computer has also led to a reverse paradigm again, where quantum computation and quantum information inspires many body physics again, and I think has already led to a lot of very interesting developments where we got different or new insights in the structure of many-body physics, right? Like through the connection to error-correcting code, through tensor networks, and various other directions. So I would say that even in the sad event that the quantum computer never gets realized in a useful form, this was already a very useful contribution of quantum computation to many-body physics. And then a second thing related to this, maybe competition between sort of classical versus quantum methods for quantum simulation. If you go beyond these quantum advantage experiments, which are really tailored to be very nice for quantum computers, where we know that quantum computers will have these advantages. If we look at, for example, the ground state problem, so computing ground state energies, which will be very useful in many situations in chemistry and material science, there I think it's really, also from a theoretical point of view, quite open what exactly the advantage of quantum computers will be. So I think it's very likely that this advantage will be there, and it's also quite likely that it will be an exponential advantage, but we do not know. And I think the option that there is not an exponential advantage, or maybe classical methods can actually be very good combined with supercomputers after more development, is also really there. And I think that's a very interesting thing to explore in the future for the field as well.
Okay, so I would like to comment actually one more point actually from the perspective of theories also working on the many-body theory. And so I'd like to also say that actually the classical simulation methods actually is also an important part for us to understand the physical system, because when we are doing classical simulation, actually we usually need to make some kinds of approximation to the system. So that actually what kind of approximation can better capturing the property of the system actually could be a part of understanding. So I would love to see actually, for example, inspired by this quantum experiment, actually if we can actually develop actually better way to actually doing classical simulation, actually it will also improve our understanding of all these many-body phenomena.
Thanks so much. That actually brings us to the end of the panel Q&A. I'm sure if the audience has more questions, then you can catch them in the break. So let's go to the award ceremony, and let's welcome Jay to the stage. I'll ask you your name. And we start with Adam Shaw. Let's go a round of applause for Adam. Then we have Yu-Hao Deng. Then Haocun Yu. Freek Witteveen. And last but not least, Anjun.